Okay, welcome to chapter 5. Actually, this chapter 5, you most learning about probability. So we have many type of probability, but most of the type that will be focusing on 5.2 and so on. So 5.1 is like a definition for probability that we're getting from the observation, direct observation. Then you can take the probability. But from 5.2, you have to do some computation on how to find probability. So I'm going to show you how to identify and compute those. Okay, hopefully it will be easy for everyone after this lecture. And I'm having, so let me check. I did record. Share my screen. Everyone see my screen, correct?
Yes.
All right, good. So let's start. So chapter 5, like you can see on my screen right here, is talking about modeling variation with probability.
Is it frozen for anyone else? Are y'all there?
Yeah.
Okay, so we just lost the professor.
Okay, I'm so sorry. Is internet our problem on my side? Let me check, share my screen. Record. What happened? Okay, right there. Okay, you all see my screen now? So maybe I start over again because I'm talking myself at first, like a couple of minutes.
Yeah, it pretty much froze after the opening screen.
Okay.
First page, I mean.
Okay, thank you. You can see the screen right now?
Not yet. For me, it says has started. It says that you started screen sharing, but I don't actually see the screen.
I see.
I can actually see the screen though on this end, on my end.
It's
Okay,
okay.
now I can see the browser window open.
Okay, no problem. Sometimes it's stuck. Okay, hope everyone can see it now. Right?
Yes.
Okay, so chapter 5, 5.1, we're talking about randomness. So the word randomness actually is talking about anything like you can select. For example, if I have like a ball of the balls, like marbles, different colors in it. So randomness, you take your hand and you put in your pot in the bag, and then you draw out something, or you toss a coin. Okay, you toss a coin, it might be a head or a tail, we call randomness. Or it can be a selected from a group of people, we call randomness. Okay, or we're testing for in class for the female or male, for example. So I select a couple of you, we call randomness. So here we are use a randomness table or technology to simulate randomness. Simulate randomness. Actually, it's just like we don't put in order. Okay, it's just like random. We take out something, we put out something. You don't know the future. Like you don't know if, for example, if you floss a coin, you don't know it will land head or tail. You don't know it. So that we call randomness. And here in chapter 5, you were learning about empirical. This one is not empirical rules, okay? Empirical rules we have learned in chapter 2 or chapter 3 already. It's about percentage. It's about like the area under the curve, like 68%, 97%, and 99.7%, 99.9%, right? Stuff like that. 95, I'm sorry. 95 and 97.7%. So that empirical rules, but now in these chapters, we don't talking about empirical rule. We're talking about empirical probabilities. So I will give you a definition later, and we were talking about theoretical probability, which is 5.2. Okay, so just, step by step. Okay, so here we are having the definitions. What is randomness? We have no predictable pattern. You don't know, right? So people are not good at identifying truly random samples or random experiments. Like I just give you a couple of the example. Anything like you pick out, you throw, you choose, that we call randomness. Probability. So probability, we have two types, like I just give it to you. We have empirical and theoretical. A theoretical, you more compute. You have to use a formula to compute. Okay, and empirical, you don't have to use formula. You just like look at by observation, based on your observation, what you see and record it, and you count, and then you got the probability. And I'm going to give you the example later. So here is used to measure how often random events occur. Right? So that's one of the definitions. Or example, when you're tossing a coin, the probability of a head is 1/2. So if you imagine you have one coin in your hand, doesn't matter, it's a quarter, it's a nickel, or it's a dime, it's just one coin. On that coin, you have a face, right? You have a face and a tail, or a head and a tail. Understand? So when you toss up in the air, you know it right away. You either get one head or one tail, correct? So that is mean when they're talking about probability of a head, then you will say, okay, I have 1 out of 2 faces, right? So you got 50%. Do you understand the example?
Yes, thank you.
Okay, so if not, stop me so that I can write it down, because some example is obvious, so I don't want to write it down too much. So this means that the coin will land on head 50%. And if I'm asking, what is the probability of getting a tail? And what do you say?
50%.
Class, what? 50%, okay? You understand? So that is talking about one coin, okay? So let me give you, that is, so this example is applied for both theoretical and empirical. If we're talking about, if I'm focusing on empirical probability, then you do experiment by yourself. You see it. You see how the coin land, and then you record it, 50%, then you're done with the empirical probability. Okay, but about theoretical, it's like, it's more a bit complex. It's like, for example, I give you like more coins, for example, then you can figure it out, or a dice. I don't know if you know about a dice example, right? It's similar to a coin, but it's more complex. It's like a dime, a dice have 6 faces, correct? A fair dice have 6 faces, but a coin mostly talking about 2 faces only. Okay, so right here, you kind of understand probability is usually they notate at, let me notate at fraction. Fraction, but this fraction is special all the time, this fraction type is not any fraction. This fraction have to all the time given you is like numerical, have to be smaller than the denominator. Okay, so here's small value over the bigger value. So in probability, because the rule is that in this chapters or later chapters, usually they're asking the probability only between 0 and 1. The probability of an event, let's say event X, the maximum value is only 1. 1 stands for 100%, and 0 stands for 0%. So you will get the probability of any event will be between 0 to 1, which means it can be any decimal number. But you make sure when you write in fraction all the time, the small value go first and the bigger value go at the bottom. Okay. Okay. Any question before I move on to next slide? Okay. No. Okay, here is a definition about theoretical probabilities. It's said it's a long run relative frequencies. Okay. Anyone understand this term, frequency? Frequency is mean repeating many times. Okay. And the relative frequency at which an event occurs after infinitely many repetitions, right? Repeat, right? So relative frequency is a term is talking about the probability. Okay, or percent. They're talking about percent. An example, if we were to flip a coin, so here you see the word is mean only one coin, infinitely many times. So even though you do many times, so we have exactly 50%. Flips would be a head, or another word would be 50% would be a tails. If you flip only one coin, but two coin will be different. Okay, two coin will be different, like way of compute. So that's why the theoretical probability is more get into compute. But I will give you an example. If the textbook will go along, they do have it, and I explain you more so that you can look back to see it better. And here, empirical probability, like I said, 5.1 for this chapter is more talking about empirical probabilities, actually. And I did give you the example about this already, right? Here, what you observe, what you see, you record it, and you got a probability. Here's the example. I toss a coin 10 times, and I get 4 heads. So when you toss 10 times, you can imagine. So let me demonstrate for you. You toss a coin 10 times, so let's toss one time first. Pretending I toss one time, my first time I'm getting a tail. I record it. The second time, I'm again, my call letting a tail. My third time, I got a head. My fourth time, when I toss my coin, I get another head. And then the fifth time, I got a tail. The six times, when I toss 6 times, I get head. And the 7, I got another head. The rest of my toss, I got tail. So total 10 times already, correct? So I recorded like that. And then they're asking, so what is the empirical probability of getting ahead in this case? And so what I'm going to do is I'm going to look at my recording, and I'm going to say, I'm going to count, use different color. Got 1 head here, 2 here, 3 here, 4 here. So total 4 head in my experiment. And then I write, so my empirical probability of getting ahead will be 4 out of 10 times that I toss. So it will give me 0.4. Another word, you take 0.4, you multiply with 100%. If you want to see this, then what do you have? 40. Then don't forget this notation right there. That's your solution for when we're talking about empirical probabilities. You understand? So another word, empirical probability is what you observe, what you have in your hands. Then you record it, you see it, you got it, and you write that solution. Okay, here they give us some kind of definitions like about theoretical and empirical probability. So theoretical probabilities are always the same value. Example, theoretical probability of getting ahead when tossing a coin is always 50%. Empirical probability changes with every experiment. Every time you do experiment, what you see, you record it, you got different value. Any question before I move on? You're good now, or you if you don't say anything, I'm pretending you don't have a question, okay? Okay, here they're explaining why we have two models. So theoretical probability might be difficult to compute. So because that's why formula will be joined with us. A lot of formulas. You have to know how to identify which formula to use. But empirical probability help us find probability right away. So on the test, there will be a lot of questions on theoretical probability, more than empirical probabilities, okay? So we may not trust the theoretical probability model. For example, the model may be based on faulty assumptions. Empirical probability can help us verify or refute a theoretical value. So the reason is we not trust because we do have a lot of, so when actually in real world, they apply theoretical probability a lot because people don't have time to run experiment like, a big experiment. For example, they want to toss like 10,000 times, for example, like that. So we cannot just sit there and count 10,000 times, right? So theoretical probability join in so that we can using formulas and technology to do it. Even though it's not very accurate, but the more that we having the outcomes, like the more that you having like the total outcome, for example, like I said, 10,000 times or 1 million in real world, and that you will get close to the actual value. Simulation. The experiment used to produce empirical probability. Actually, it's very simple for 5.1, right? It looks like they introduce us to probability, so we will have to prepare. So now 5.1, you understand empirical probability already. Okay, so 5.2 is more difficult. So let's go on 5.2 now. Any question on 5.1? No? Okay. Okay, 5.2, finding theoretical probabilities. So, so here are the key terms for this. Find theoretical probability of equally likely event. Okay, this is one of the terms. from the theoretical probability, and you find the probability of the complement of the event. This is another notation later. So these two different, okay? These two are different. And we will learn how to use some rules for this in this 5.2. So here is the artifact about probability. So first, you notice the symbol that they're given us. The probability of the event X all the time will be only from 0 to 1. The notation equal sign involving is mean the probability can be a 0 or can be a positive 1. If you, when you do the math, you compute, you have a negative value, you're wrong. But if you compute, you got 1.01, 1.02 or something like that, more than 1, you are wrong too. So all the value for probability only from 0 to 1. Okay. So, and probability can be expressed as fraction, decimals, or percents. Like I just demonstrate to you, fraction in this case, I would like to emphasize that the small value go first, the bigger value will go next. But if you got the switch over, you will get like 3, like more than 1, so that it's not correct. And third, an event has a probability of 0 only if it can never happen. It means, for example, you got a 0 when I'm talking about, for example, I'm talking about the a coin, and then talking about a dice. A coin and a dice, they're not related, so their probability will be a 0. Okay, or they don't have anything in common. So two events don't have anything in common, you got a 0 probability. Fourth, an event has the probability of 1 if and only if it's certain to happen. It means 100% happen, then you will get a value is 1. 1 represents for 100%. 1 is mean equal to 100%. Okay. And we do have some notation as following. The events are usually represented with uppercase letters. Actually, for me, it can represent anything, okay? Not just uppercase. It can be a sentence. It can be a terms. It can be a lowercase event. Depend on the story that given to us. Then you recognize this is event A, event B, or it's talking about pencil, or it's talking about a meal, or it's talking about pizza, stuff like that. So you have to recognize that. And those we call events. So when we're talking about probability of the event, you have to write as P represent for probability. And then you must write a parenthesis. And then you write the events in here. And then you close the parentheses. Okay. So when you compute, you will put the equal sign. Don't forget this, because if you are not following this, I might take off point from you. Okay, so you need to be careful. The events in here is important because you need to know how to identify the events. What talking about? What probability talking about? Then you will compute that. You got a value here. I box the value. Okay, you got a value either in fraction or decimal value. So let me say in fraction, for example, A over B, right? Actually, our probability will give have to be a number, a value. An example will be the following: toss a coin, and we let A represent the event. The coin lands on heads. Like I said, see that? If you let your event at the beginning as a sentence like this, a coin lands on head, then you are allowed to write P of A, but you have to let me know, right? If you're lazy to let me know at first, and then you have to write the whole thing in, which means you have to write probability of coin lands on head. Okay, so in this class, if I'm talking about coin head and tail, you can write shortcut. Okay, you can write a bit shortcut like this. Probability of head stand for H. But hopefully it's not like too many stories that I'm writing about. Sometimes I'm talking about high school students. So H it might be like messing up with the head. So maybe when I'm talking about high school, I would like you to write HS. Okay, for stuff like that. Actually, hopefully you understand what I'm saying. If you are afraid, then you just write heads, okay, or H. When I'm talking about a coin, then just H or T. It's okay. Any other question? Yes, go ahead.
Question just in terms of like if we're writing this on the test, then do we need to put like H equals heads and then write P in parentheses H, or would it be obvious from the question so we wouldn't have to identify what the letter stands for?
Yeah, I think when I'm talking about coin, then right away I understand H stand for head and T stand for tails.
Okay.
Yeah, just H and T, unless I combining like too many like coincident letters, the same meaning, the same, like the same first letter, then make sure you identify for me to understand different things. Okay.
Great, thank you.
Okay. So here just again some more definitions. You need to understand the definition first before we jump to the real example. Okay. So here we're talking about complement of an event. Complement of the event all the time, they have a big letter represent for the event A, and then small c on the top. Okay, and you're done. That's the complement. And the complement actually just like the opposite meaning with the event. For example, like you can see, event A represent for a coin lands on heads. So A complement, which is A raised to C, small c, meaning coin doesn't land on heads. That's it. Another word is land on the tail, right? Like that. That's a complement. So here the example of computing how you can get shortcut for the probability of a complement. So probability parentheses A does not occur, close the parentheses, equal to 1 represent for 100%, which is the whole thing, right? Minus the probability of A does occur. And again, like I said, any probability will be smaller than 1. So 1 will be considered might be the biggest value in probability here, right? Because A stands for 100%. Minus some percent, you'll get a value of some percent. Okay. Another word, they write shortcut, P of A raised to C, close the parentheses, equal to 1 minus PA. So the example, let event A represent the event talking about the candidate wins an election. So suppose that the probability of the candidate wins an election is 70% or 0.7. So then A complement, which means the people not win the election will be P of A raised to C equal to, you take 1, which is the whole thing, minus P of A, which is 0.7, you got 0.3 left, which is the probability that the candidate does not win an election. That is the example of the A complement and A event. Again, any question, please let me know in the chat or speak out loud right now if you want. Sample space and events for equally likely outcome. So what does it mean, sample space? Sample space, they're talking about the set of all possible equally likely outcome of an experiment, an example of sample space. The sample space notation usually they're going to use is this, but we're not using a lot sample space in these chapters. Equal to a set. So this is notation of the set. So depend on what story that we're talking about, then you will write all the event, all the possible equally likely outcome in this box. So an example I can give it to you is, let's do an example quickly. You toss 2 coins at a time. Okay, so 2 coins, 1 time. So now, if the question asking, write out the sample space for that situation, then what I'm gonna do is, so first I'm gonna do my scratch work. And then I can write my solution in this set. So toss 2 coins. So let's imagine we got 2 cards in our hands, right? You toss up. It's possible that they can give it to us 2 coins. The first time, 1 time only, toss 2 coins at 1 time. So you got, I'm pretending you got 1 head and 1 tail for the first toss. Right? So, but right here, they're talking about equally likely outcome of the experiment, which means we're not talking about like, you toss like how many times you want. So this is not empirical probability now, right? So now you can repeating your experiment by using 2 coins. Now, when you're repeating your experiment, then you are having, you toss 2 coins in the air and it might land. The first coin is head, the second coin will be, I'm sorry, the first coin is tail, the second coin will be head. And then you do it again. You try to do as many as you can, as long as your event is not repeating, okay? It has to be different for 2 coins. So now I've tossed 1 more time for 2 coins, then I'm going to get tail, tail. 2 of them. The first coin is tail, the second is tail. I do it again. I got head, head. Okay. And I do it again. It's come out head, tail, for example, and so on, or tail, head, and so on. But however, like I said, the event should not be repeating. It looked like my first toss is head, tail. And my 5th toss right here, I'm having head, tail again. I should cross out one of the event. That's the same. It's not allowed to be repeating. When we're talking about finding any probability of, we're talking about equally likely outcomes of the experiment. So we only have 4 different events. So we got 1, 2, 3, and 4. You understand what I'm talking about? Now you're going to record it for sample space, head, tail. You put commas to separate the events. You got TH, that's for the second event. You got TT, that's for third. You got HH, that's for last event. Again, the order of this this event doesn't matter, but we matter the order of each coin. Okay. So the sample space for toss of 2 cards at a time, I'm having the following set, which is this we call omega. So this notation for omega, this is quick letters, stand for sample space. And then you write equal, and then you write the set, and you write events inside like this. So that is how sample space. And we call all of this, we call each of this event is equally likely outcome of this experiment. All right, any question before I move on?
Yeah, can you repeat what is the omega symbol? What does that mean?
Here is a sample space.
That's the sample space, okay.
Mhm.
And then the in brackets, is that called a set?
Event.
Oh, that's the event. Okay, sorry. Thank you.
Mhm, mhm. And this curly bracket is a set.
Yes. Okay, it's a set, but then it's also the event.
Event inside the set.
Okay. Thank you.
Mhm. Okay. Can I erase it now or you need time?
Okay.
Okay. So you can rewatch this video too. When we're talking about theoretical probability, all the time we're talking about equally likely outcome events all the time. It's like that. It's like this. Okay. So here the example of the sample space, they have different example. They have talking about a die. Roll a fair die one time. Okay. The sample space. So here in the textbook, they don't write a set, but usually in reality, you have to write a set, right? Like this. Okay, so we are having, for example, you can imagine a die, all fair die, you having 6 faces, correct? You have 1 dot, right? On one face, we got 1 dot. Another face, you got 2 dot. Another face, you got 3 dot. For those who don't get what is a die, you can Google it to see the shape of it. And on the dice, they don't have number, they have just dots. So here they write it down. So when they roll a die, that die only land on one face, right? You can see only one face on the top. And then you're recording the value. And again, all of this event, we got 1 dot, 2 dot, 3 dot, 4, 5, and 6 dot. Maximum is 6 dot. So total of the sample space for the roll of dice, one time, we're talking about our die and one time only. We're having 1, 2, 3, 4, 5, 6 represent for the faces, the number of dots on the faces of each on the die. Events, roll an even number. So now when they're talking about, so here you can see, go back to the sample space, you can see 1, 3, 5 represent for odd value. 1, 3, 5 represent for odd, right? Odd number. 2, 4, 6 represent for even number. Agree? So if they're talking about only the event that is for even number only, then from this set, from this experiment, you will see 2, 4, 6 only. And if they want you to find probability of this, probability of the event, even number. Can you tell me what is it?
50%.
50%, that's good. Or you count the event number will be 2, 4, and 6. You got 3, right? 3 event, correct?
Mhm.
Out of how many total event in the sample space?
6.
6. So total would be, you reduce, you got 1/2. Or another word, 50%. That's how you compute probability, theoretical probability. Okay. So another word, another example, they say, roll a number less than 3. That's the event that they're talking about. A number less than 3, you're thinking about 1 and 2 only, right? So if we want to find the probability of a number less than 3, a number less than 3, I would say x less than 3 for small x less than 3. So in this case, the event x roll a number less than 3 and represent for the value is 1 and 2, which means you got 2 events out of total is 6 events. You reduce this, you got 1/3, right? It's 1/3. Then change to decimal number, you got 0.333 something. 333 repeating too many times, you put a bar above that. Okay. Any question? Okay, no question, and then move on. If you need time to copy it, please let me know so that I can wait for you. We do a bit more lecture than I would do. I will let you do join in a group to do practicing. Like, hopefully you can. Are you taking note a lot? I'm just wonder.
Yes.
Okay. Okay, so this is using a sample space to find a theoretical probability. Okay, like I just focusing on, I did some example ahead already, right? So this is we having a formula. So P of A equal to number of outcome in A, which is the number of the event, right? Divided by the total of the possible outcomes, which is all the event in the sample space. A more example, you roll a die. So let A represent for the event getting a number less than a 3. So we did this already together already, right? We got 2 outcomes less than 3, which is 1 and 2. Probability of A, which means probability of getting a number less than a 3. You have 2 events divided by all total 6 outcomes. And you reduce, you got 1/3 or 33%. We did that in previously. Another example, using the sample space to find example is a family has 2 children. So they want us to find a probability that both children are girls, right? So 2 children. So your job, you have to figure out how many total outcome in this case. So let's do this together. So in order to know, so when you are doing the test, you only receive the sentence. Your job, you have to find all the sample space or total outcomes before you find probability. That's your job. So now focusing on how to understand this. One family, right? talk about one family and they have 2 children. So they don't give us like that family have 2 girls, 2 boys, or 1 girl, 1 boy. The first one is girl, the second one is boy, or the opposite. They don't give it to us. So now you have to write all possible outcome of that family has. So in my mind, another word, we have to find the sample space, right? Or another word, we find the total outcome. So pretending the first one, you just thinking like, okay, that family, maybe the first one is a girl. The second one might be a boy. Some people say, okay, how about maybe that family have the first one is a boy and the second one is a girl. Or maybe that family have 2 girls. First one is girl, second one is girl. It might be possible is the first one is boy and the second one is boy as well. So when you are thinking like there is no possible outcome that I can write, then can stop, because it should not be repeating. So these 4 events different, right? So this we call total outcome. We got 1 outcome, 2 outcome, 3 outcome, and 4 outcome, or 4 events. So the question they're asking, find the probability that both children are girl. It means probability of both are girl, you can write girl, girl, right? Or you write a word, both girls. So now you look at your total outcome, you see, both girl only this event. You write one event only, divide over what? Total is 4 events, possible 4 events. This will be about 25% or 0.25. Okay. So if another question that I would ask, I would like you to find me the probability that this family have at least 1 girl. What do you think?
3/4.
3 out of 4. How come?
Because in 3, there's 3 of 4 outcomes.
Yes. Right. So let me circle all the event have at least 1 girl. At least 1 girl is mean 1 girl and up. Agree? So we got this event. So the second one, I think boy, girl, right? Boy, girl. The second event, this is girl, girl. When I erased it, I accidentally erased this too. And girl, girl, right? Boy, boy, we don't count. So got 1, 2, 3 event. 3 out of total is 4. I got 3 out of 4 or 75%. Does it make sense to you? Class? Okay, you all good?
Yes, thank you.
Only you.
I saw Cynthia gave a thumbs up, I saw.
Oh, really? All right, class. Okay, hope you understand this probability. This require you to think a bit more, right? You need to find all of the outcomes and then count and compute. So this is formula. So remember that formula, okay? The formula that in previous page that they give it to us. And here the example to support you to understand that formula, how to use it. Okay, we're talking about combining events now. So combining events in probability, they're using the word and. Right? And that's mean like both, right? So an event belonging to A and B must belong to both A and B. Another example that I can give it to you is my event A, for example, this circle. And I'm having my event B, that's using red circle. The word and here is mean they both has it. Right? So this will be probability of A and B. Another way to writing it will be probability of A and then a curve, a round curve like this, and B. That this one is notation for and. This one, okay? It's like and, correct? But it's not capital N, it's a round shape. Downward. Example. If event A represents wearing a hat and event B represents for raising a hand, then someone in A and B is wearing a hat and raising a hand. Can you imagine that? The story will be maybe next picture. Right there. They're talking about event wearing a hat and raising hand, correct? So in this group, we have 1, 2, 3, 4, 5, 6 event or 6 people, right? 6 obvious people. And this person, both when we're talking about raising hands and wearing hat, only she and he, right? So you can find probability will be 2 out of 6. So they have name underneath: Mike, Rena, Maria, Ellen, John, and David. So this is just the example that talking about they're using the word both, we're using the word and, so that you can see it how is work from picture. But sometimes see you have to like imagine more. If we're talking about like a dice or something. The word or is mean either one, right? So in an event belong to A or B must belong to A or B or both. Okay. So the word or in this case is mean that if you imagine, so let's talking about that picture again. So later I'll go back to that picture so that you can imagine it. And hopefully later we have more example in this textbook. If event A represents wearing a hat, you can imagine the people wearing hat. We have 3 people, I think. And event B represents raising a hand. Only 2 people raising a hand. Right? Then someone in A or B is wearing a hat or raising a hand or both. Okay. So people wearing a hat, right? Hat we got Rena, Maria, and David, right? However, this we're talking about event that having wearing a hat and raising a hand at the same time. So what we're going to have the formula will be the below formula. You will see it. they have been the formula for and or. So to be more clear, I will give it to you later. You will see it and you should write it down somewhere. So a person is selected at random from this group. We have to find the probability that she or he is wearing a hat or raising his or her hand. The number in the sample space, we have 6. And the number raising hands or wearing hat or both, we are having the following. Rina, Maria, David, 3 people wearing hats. So here, even though it's not given us a formula yet, right? It's not given us a formula. So it's very, I don't know, it's difficult for you to figure it out or not. Hopefully it's not. So you can see right away, Rina, Maria, and David, they have hats and raise hand at the same time. So the word or in here is mean. I'm gonna give you the hint right here so that you can imagine better. Okay, I'm having, so we have 3 people wearing hat. We got 3, right? 3 people wearing hat. So, but or the word or, wearing hat or raising hand, we have 2 people raising hand. So in reality, we have the event A represent for hat, event B represent for raising hand. You have P of A, the event A only. You add with the probability of the event B, but then you have to minus the probability of event A and B. A and B. Okay, like this. This is a formula for P of A or B equal. So let's compute carefully. So look at the picture. I'm going to see probability A. A represent for wearing a hat. I'm having the following. Wearing hat, which is PA. Let me write out PA. What do I have? Wearing hat 1, 2, 3. Have 3 out of 6. Understand? Probability of B, PB. How many? 2 people raising hand, correct? Which is 2 out of 6. So how about P of A and B? Can anyone tell me? Probability of A and B. Remember? A and B, what do you mean? What does it mean? Wearing hat and raising hand at the same time. So how many do you see?
2.
2. 2 out of 6. So now I plug it in. So I'm having PA, which is 3 out of 3, 3 out of 6, minus, I'm sorry, plus, the formula plus. P of B is 2, 6, minus, take away both of them that raise head and wearing hat, raise hand and wearing hat, 2, 6. So now you do the algebra. What do you have? You've got positive 2, 6 minus 2, 6, right? You cancel out. You cancel out this term, correct? You've got 3, 6 left. Another word, 1/2. Or 50% or 0.5. Or equal to 50%, okay? Is it clear?
Yes, thank you.
Thank you. All right. So let me move on to next page to see what happened, okay? So usually for face-to-face class, I'm done with my lecture for the day. You will do practicing. Okay, however, I will try to do some more, try to guide you to understand this formula first. And then I might give you break into group to practice some of the example that I can give you, okay? Okay, this is more bit harder, okay. So maybe I'm gonna give you, let me see. Now let's finish this and I give you exercise. So finding probabilities from two-way tables. Two-way table is this type of table. Okay, we've got two-way table. They have different name anyway. They have different name. They have many names. Some people call this pivot table. Some people call this two-way table. Some people call this I think contingency table. Different book use different name. Okay, so here is this following the table inside. Below here, yes, you notice we've got in a marriage, the husband should work and the wife should take care of home. So the following table summarize the data collected. We got happy, okay, happy. We got total people who happy with this is 991. Right, total, you look at the total column. This total column right here is they adding from the happy, both agree, don't know, and disagree. They add all up to get the total of the people who happy, and that agree, don't know, and disagree, like everyone. And the second column, as you notice, is unhappy, which is the same thing. They add all up. They got 155 for unhappy, with both agree, don't know, and disagree. So the number is 1146 here is the entire total, both happy and unhappy. Okay. And we do have the total of the agree. The total of the agree, we have both happy and unhappy add up to be 287. Don't know, both happy and unhappy, we got 95. Disagree, we have happy and unhappy, we got 764. This all value add up, you got 1146. So this again, you got this, add that to get 1146. So when you are doing it, you make sure this 1146 have to be the same, right? For vertical and horizontal when you're adding up. So this number is the entire total. Next. So now we're going to find the probability at the following. Okay, so they're asking us, suppose a person is randomly selected from this group. They want us to find probability of happy and agree. So again, go back to the definition. The event having the word and, like I gave it to you at the beginning, at the we did the definitions. It means they have to join, right? They have something in common. So now we check. Should the event happy? So look, I'm crossing the event happy. Happy right here, right? So I draw a line, straight line. This is the way that I'm using two-way table to figure it out, the word and. The word and is mean they join, they have together. Now the event agree. I look at agree. Agree is vertically. This is agree, right? Now I draw a different color. Agree, I draw it down. See that? So can you tell me what happy and agree they have in common? Can anyone tell me when I cross that?
242.
242, thank you. So that means the solution will be equal to, do you see that I'm crossing? Say, I'm crossing it, right? It's right here. We got this together. So 242 divided by out of this total, right? 1146 will be my solution. So when you're doing the work in the task, I would like you to convert this into decimal point, decimal place, okay? Even though the textbook is they want to save time, but like when I'm grading it, I want to see decimal value so that it's easier for me to compute. I take 242 divide 1146. I got 0.211. So you round to 100 place, which means 0.21. Okay, that's what I need. This, and you box it. All right, class. However, you must show me this fraction as well. You must show me everything. That's how you show your work for N. How you show your work for R, like I said, I would like you to see the formula that I give it to you. Okay, so I'm going to demonstrate for you. Okay, that's part A. Any question? And it's kind of easy, right? You just pick the part that they have in common, and done. B, probability happy or agree. Happy or agree. So now they're using the word or. So make sure when they're using the word or, you make sure that you write down the formula is a bit longer. Or you can see directly right there and then write a value in. But because I'm doing lecture, so I write carefully. I write more detail. P happy. Let's say in this case, to make it short, I write PH plus P A, just stand for agree, minus P of happy and agree. That's my formula. Now my job, I have to find a probability of happy first. Before that, I'm going to erase this table. So probability of happy, what do I have? Okay. The total of happy that I'm having is this, right? Happy all the way here. To find probability of happy, I got total is 991 out of 1146. The entire total, right? I add with probability of agree. Use different color. Agree total. Total I'm having is 287 divided by 1146. Make sure you're having the same denominator so that you can add or subtract. Easier. And then take away P of H and A. P of H and A you found in part A. We got 242 over 1146, or you can see that they join right here, right? Now you do the math. When we're done with the math, they all have the same denominator. You just solve the top. I got 991 plus 287, and I take away 242 equal 1036. 1036 out of 1146. You divide 1146, you got 0.9. So that's equal to 0.904. So you arrive to 100 place, which means 0.9. Any question? Please let me know right away so that you don't forget. I pick out this question to make it at the study guide. So hopefully you understand this part and do well on the test, the second test. Okay, no question. Part C, agree or don't know. So now your turn to do it now, please. How many people are here? Okay, so since we have a small group, so please, you can talk together for a few more minutes how to compute this part C and give me the solution now, okay? So I give you, let's say 4 minutes to do this problem. Go ahead and do it now by using formula my solution from part B, how to do it.
So we have to like, I mean, because the easiest thing would be just to add 287 plus 95, but then that's not showing the formula. So we have to show the formula. Is that right?
Yeah. We have to. For the word or, it's very difficult that you can look by eyes and then add it right solution right away. Even me, I cannot do it by that way. The best way is you using that formula and write it down. Anyone have solution?
I'm confused because,
Oh,
okay, so the possibility of agreeing would be 287 over 1146.
yes.
And then the possibility of don't know is 95 over 1146.
Mm. Good.
But then I'm confused now because then, I mean, they're both going vertically now. There's not like
Uh-huh.
the only intersection would be just if you add up 287 and 95 next to each other. But then that leaves me with 382 over 1146. But then it would be 382 over 1146 minus 382 over 1146. So that can't be right.
Okay, thank you for sharing. Let me see if anyone have other idea. Any one of you beside Connie?
Come on, y'all.
I'm stuck in that part too.
Okay. Anyone figure it out? Think a bit more. I did talk about this already. Okay, no?
I mean, I know the answer is
Yeah.
33%. I just
Ah.
doing it the formulaic way.
Mhm, mhm.
I don't understand what I'm subtracting.
Okay, so let me write it down in detail so that you can see. So I write out a formula. I have probability of agree, right? Plus probability of don't know. Don't know, say DK. Minus probability of agree and don't know. The hard part is that part, right?
Yes.
So you found probability of agree is, you said 287 over 1146. You add with don't know is 95 over 1146. Now is this part is hard. So now go back to the example that I'm asking you. I'm talking about a dice and a coin, right? A dice and a coin, they're not related. So look like you are saying this in this table, agree is vertically, don't know vertically. They're not really like joined. They don't have anything in common, right? It's like separate things, correct? So the joy part between these two is a 0. We call this agree event and don't know event. We call this will be a name we call a mutually exclusive event. And that's a name. So they don't join, they don't have anything join in common. So you will be subtract 0. So the answer again, like you are saying, you got 287 plus 95. What do you have?
382.
Okay, 382. Okay, 382 divided by 1146. And you said you got 30 something percent?
It's 33.3, so we could round it to 33%.
Okay, okay. 0.33. I need decimal, right? Okay, that's all. That is now you learn new term. Again, if they don't join, like this case, we call mutually exclusive event. I think the term will be at the bottom, next page. Okay, so any question on this part? How to work out this before I just move on? Okay. All right, so let's move on. Let's see. You can take a quick picture if you want. So you can take note. All right, move on. Oh, look, they're having the solution right here too. See part A, we got the same. Part B, we got the same too, right? But they don't really write down the formula yet, but I do need you. The reason they don't write it down is because they want the scratch work right there, just in front of you right there, the scratch work. But that's, to me, that's not helpful. I don't know if it's helpful for you, but for when you're using the formula, it's applied all everywhere. They apply like more difficult problem. Okay, so I recommend you using the formula that I gave it to you. Okay, so we are having 382 over 1146, and that equal to 0.33. Okay, it's just similar. So hope it's help. And the word mutually exclusive event right here for you. So the word here saying that, let me erase this. They explain to you the word agree and don't know. We call mutually exclusive event. This means they're not related. Okay, and you can tell the word happy and unhappy. Again, they are mutually exclusive event as well. And the word don't know and disagree, they are mutually exclusive event. Or the word agree and disagree, they are mutually exclusive events. Because they're not related. It's not joint. They don't have anything in common. Now the rules. Okay, good job. So the rule is right here. So that is what you need all the time. For the event we call mutually exclusive, is mean the probability have to be a 0. Okay, all the time. And sometimes they do a shortcut. When you recognize that events are mutually exclusive already, you can go ahead when you're writing to find the probability of the event, mutually exclusive event, you just take PA plus PB. You don't have to subtract 0. Okay, but you have to let me know they are mutually exclusive events to do so. Okay. Okay, so I think for the example two, let me see how many more slides do we have. We have this slide, for example. I might let you do it, apply by all the formula that we have gone so far on the above here. Okay, and understand A and B, what does it mean? And you want to do a practice on this one for me, please. Okay, we are having the experiment, roll a dice, roll a first 6-sided dice, and I need you to find probability of rolling an odd number or a number greater than 3. So let me highlight this, the word or. Okay, so there's a practice, and roll part B, rolling a number less than 3 or rolling a 6. So think about this a bit harder. Okay, so okay, let's do it until 12:50. Hopefully you've done that part, and then we will keep solving this next class. All right, Thursday. So section look like section 5 part 2 is very long, right? Okay, go ahead and do it now and let me know if you have any question before I end the class. And starting again, I do more lecture on this next this Thursday. The due time for this lecture is the following Thursday, right? The following Thursday next week. So you have plenty of time. All right. So let's work together. You can share what you have, what you thought, We have 6 people. Exclude me will be 5. Share what you think, what you do, how you do it. Apply my formula. That's it. When you have question, I will turn on the recording. So now I will turn it off for a while. Yes. So now we're gonna get a solution from Connie. We are having part A is 5 out of 6. So the rest of you, what do you have? Can you please share? Please join with us. You need to practice to understand it, right? To understand the lecture. I'm waiting for more people to reply. Okay. Good. Yeah, rolling less than 3 and a 6 will be mutually exclusive. Correct. So any other thought? Let me know if you have got the same with Connie. Or you got different answer. Can you please type in the chat? All right. All right, so let me go over it. Part A. You know it, the outcome will be 1, 2, 3, 4, 5, and 6, right? Right in short. So rolling an odd number we got 1, 3, and 1, 3, 5. So it's mean probability of 1, 3, 5. I'm having 3 out of 6. Okay, and probability of a number greater than 3. Greater than 3, not equal to 3, right? Greater than 3. Oh, greater than. So what do you think? What do you interpret the word greater than? Because there's two cases. There's 2 meanings when you are talking about greater than.
Just anything above 3. So it'd be 4, 5.
Yeah. So make sure that what is mean, the word less than and greater than, less than, you have noticed in the in previous slide is mean only 1 and 2, right? So greater than is the same thing. You don't include 3, okay? So that would be 4, 5, 6. This is 3 out of 6. Okay. The word or. So look at the value that you are having odd is 1, 3, and 5. We got 1, 3, and 5, and greater than 3. What do you think? What do you think that's in common? So let me see odd and greater than 3, right? What do you see? What do you see in common? What that 2 set in common is a 5. Understand? Only a 5 is the same. It's mean 1 out of 6. Okay. The probability of a 5 is 1 out of 6. So now you combine by using the formula. We're going to have the following. So we're going to have probability of rolling an odd number will be 3 out of 6. So I write in short. So 3 out of 6 But when on the because I don't have space, so I do this way. But you need to write the whole thing out for me, okay? You need to write P of 1, 3, 5 plus P of 4, 5, 6 minus P of 5 on the end of that too. 3 of 6 plus 3, 6 minus 1, 6. 3 plus 3 is 6 out of 6 minus 1 out of 6 will be 5 out of 6. Right, will be solution. Then convert this into decimal. You got a value. Is it what Connie had? Connie had. Part A. Good. So 83%. Part B. That's part A. Part B, I'm using blue color. So I'm having rolling a number less than 3. You can imagine will be P of less than 3 is 1, 2. Plus probability of rolling a 6, right? Rolling 1, 6 is 1 out of 6. So minus, because there's the word or again, that's minus this 2. But these two look like they are mutually exclusive events, so that's minus 0. Or you let me know these two events are mutually exclusive, then you don't have to take away 0. So we have 2 out of 6 plus 1 out of 6. This is 3 out of 6. This gives you 1/2 or 50%. Okay. So that's how you do for this example. Again, on the test, I write more questions like this. I mix them up, like change different names. And you can see more on the study guide that I have written and posted already. So you can check that out and practice along with those examples. And that's it. All right, no problem. All right, so but make sure you do okay on on the test, because that will be takeoff point for the algebra stuff. All right,
It was such
so-
happy math on my
Mhm.
part. Oops.
yeah, no problem. So okay, so that is it. That I will continue lecture on this section 5.2 next time. All right.
Thank you.
Okay. Yes. Any? Okay, class, see you on Thursday. If you have questions, you can stay and ask. It's my office hour.
Thank you, Professor. I understand it now.
All right, good job. Yeah, have a good day. Bye-bye.
Bye-bye.
Bye-bye. All right, let me stop recording to take question. Okay, let me see.